Then, see, even within the last 30 years, look, say more than 15, say, damaging earthquakes that sustain the human injuries and the property loss and so forth. And then, say, Japan shaken everywhere once in a while. One is this, 30 years ago, 1995 Kobe earthquake, numerous structural damage we saw here. And then 2011, 15 years later, Tohoku earthquake occurred, and that experience invoked a societal resilience as we found it not possible to protect the society by 100% once big one comes. See here, the washed away towns and the villages. Unfortunately, this happened. So then this way, say, we keep receiving earthquakes in the land of Japan. Then one effort, and one big effort is to characterize earthquake occurrences and strong motions. In other words, how big ones come where and so forth. But to this end, say the country of Japan is deployed with thousands of sort of sensors to measure grounds and sometimes underground and sometimes say even the seabeds. But anyway, few thousands say sensors just being monitored, so forth. This is on the say earthquake demand side. On the earthquake, the resistance, the structure side. This is a generic, say, strength, vertical axis, deformation, relationship. So in other words, in the beginning, no pointer, unfortunately. Okay, now here's a pointer, really small, but that's okay. Well, anyway, say all structural, civil engineers, you know that. Say first, everything is fine. But then gradually yielding begins, still all right, but somewhere damage begins and more damage and to the collapse. That's a life, right? Then I think that our effort is to increase the strength, make our structure stronger and more ductile. And there are many ways to achieve that. For new construction, say let's use new materials, or new or hybrid structures, or passive active controls, or base isolation, those technologies to enhance the seismic capacity of our buildings. And for the existing structures, say the advanced diagnosis methods for seismic capacity and according retrofits and so forth. But anyway, the efforts continue to raise the strength and to raise the ductility and so forth. So that's Japan, and we can't escape this. And then here is a little bit of myself. Say Professor Rikus already gave enough, therefore I can almost skip. First, I graduated from Kyoto University and I came to Lehigh, happy 4 years, and then returning to Japan, I joined the National Research Institution called the BRI, Building Research Institute, moved to Kobe University and Kyoto University, and then time by time I worked for the Cabinet Office of Japan to lead some of the national research. But sometimes, as indicated by Professor Rikus, I worked for E-Defense, a big jumbo shake table, whose details I'll talk to you a moment later. But anyway, pictures of 3 gentlemen. Minoru Wakabayashi, my mentor in Kyoto, and then he was a visiting scholar of Lehigh in 1955, long time before you're born. But anyway, and then the person in the middle is Professor Bruno Türlimann. He was professor of ETH Zurich for many years. He was also Lehigh, right? The professor one time. And the last one on the right is Professor Liu Lu. He was professor of this university until 2015 or so. Those 3 gentlemen were friends, and their friendships somehow brought me to this happy place of Bethlehem, Pennsylvania. Well, in the interest of time, I'll skip the details, but there are funny stories somewhere. But anyway, thanks to those gentlemen, I was able to come and I was able to enjoy myself when I was 20s. Back to this, say, the issue of today. After I returned to Japan, I joined a national research institution called the Building Research Institute. And then the institute, huge reaction wall and the big reaction floors. And then they could do the real test, scale tests for 6, 7, 8 stories of the buildings and so on. And then I had a happy time, but then 10 years later, I moved to Kyoto University. And then I was, I worked for the management and operation of medium to small size of reaction wall, much shorter and also narrower. But anyway, so I went to join the Kyoto University, and I was engaged in experimental work using small size, loading systems. Few years later, in conjunction with the post-Kobe research, and then my university gets some fund to develop a medium-sized shifting bam, bam, bam. And then at that time, Kobe earthquake, much damage. And then one reason was the big velocity. So therefore, the post-Kobe research facilities, the development, naturally, big velocity was to be produced. But anyway, I got engaged in a dynamic test for small size. And then about 10 years later, I was asked to join E-Defense to found and operate this big jumbo facility. Again, this dynamic. So those are the 4 labs I spent my life as a professional. And then, however, these pictures are a little misleading because the reality must be like this, much smaller. So then it's small, big, big. Okay, and then further, this picture gives us an interesting classifications. First, those 2, small. Those 2, big, size. Now, not only that, look at the vertical axis, slow. So if anything, actuation means applying the loads and so forth, slow, versus this one, real time, bam, 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 fast. So here it's an interesting combination of slow versus fast, small versus big, a total of 4 combinations, right? I was involved in all of those 4. And I got some special experience with those 4 facilities. That experience of mine is something that is a story that I would like to share with you today. So far, okay? Big versus small and fast versus small. Okay, small versus fast. Now let's go with the big one, slow. This is a jumbo testing facility at Building Research Institute. One thing I want to emphasize is that this was not built yesterday. 1980 means 45 years ago. And 25 high reaction wall and 25 by 20, well, number not important, big anyway. So then floors, and then the test bed could can accommodate 6, 7, 8 stories of buildings, real scale, and then many actuators attached and push and pull, and then see how they behave and so forth. Now this is a loading and measuring systems. Too small, in characters, but anyway, many wiring permanent to connect the sensors to the loading, to the data processing system hydraulic power here, and then servo control, and also the computers to control, servo control and the measuring and so forth. And then this is the system made available 45 years ago. And I worked as the most junior member of this. And then we're trying to incorporate the then relatively new technique called pseudo-dynamic test, or also known as online computer control method, now called hybrid simulation. We were trying to deploy the method of hybrid simulation into this big system. And what is hybrid simulation? And this is something that we may beat shake table tests, or this is experimental techniques for simulation of earthquake response behavior and the structure, element, and systems, or combination of quasi-static loading tests and time domain numerical analysis. And interestingly, the method was developed by a group of Japanese over here. The initial development was in late 1960s and early 70s. And this is a picture of the hybrid simulation. I know that many of you, and particularly those working for Atlas Center, are very familiar with this. They know better than I know. But nevertheless, let me briefly explain what it is using my old language. And suppose we have an, three-story building whose response under earthquake we want to know, okay? And then if it is an elastic system, so that's easy. There's simple numerical or analytic solutions available. But if, it exhibited a strong nonlinear behavior beyond yielding, like this, then it is rather difficult to model such hysteretic behavior. Then the idea was, okay, let the test attached to the equations of motion solve the hysteretic behavior. How? Now, we set up the basic equations of motion to represent this system, and then we use direct integration with respect to time, and then suppose we are step n, and then we predict the displacement for the next step. Then we apply the displacements to that target displacement, and then when we attain that displacement, we measure the reaction forces, F. And that this F, the reaction forces, are fed back into the computer and to solve the equation of motion for the following step. By repeating this push and get and reaction force received and the computation advance and so forth. Then in the end, we can obtain the complex hysteretic behavior, how it works, and at the same time, the three-story test structure behaved as if it was subjected at the specified degree of motion, but in a very slow speed. So that's the essence of hybrid simulation. And then at that time, we were too brave or maybe audacious to apply this simulation method to real scale 6-story steel frame over here. It was in full scale, 6-story, 2x2. And as I wrote in the bottom, it was the days when no personal computer, no PC, or no CAD available. So then look at the figures. You understand the figures? Human made a drawing using drafting pens. Okay, that's the time. You understand what I'm saying? Okay. No PC, no graphics, no nothing. But anyway, then what do we, okay, here some pictures. This was one of the actuators that can produce 1 meter of the stroke plus minus, or high resolution digital display transducers, and then many sensors to measure local behavior and so forth. say, as I said at the bottom, after 40 years, they still look sort of modern, so not so bad. But that's something that I was engaged. Then back again to this full-scale 6-story brace frame, how we did it. Now, say loaded horizontally using 7 actuators, because although 6-story, but we put 2 actuators at the top to avoid, say, torsion. But anyway, those multiple actuators synchronize with hybrid simulation control and push, pull, push, pull, push. And then this is the result we obtained. Time history of about 10 seconds. So then it was good. One notable thing is it took 5 working days instead of 10 seconds. Why? Because intentionally speed was down, slow, slow, slow. More important, when we reach a certain displacement at the peak, okay, we stopped, we paused the loading, held the displacement, and then the engineers go to this, go into the specimen, check damage, and so forth. So it takes an awfully long time. So in the end, in order to simulate the 10 seconds of grab motion, it took 5 days, but never mind. Say 5 days is short enough. But this is the system that I worked many years ago, and then again, this is right. It's a big but slow loading system. Next one is now 10 years later, I moved from this big institution to to a university, and then now I was able to get this system when they're already old, but okay, instead of 25 meters, now 5 meters. And then instead of 20 by 15, okay, long enough, but so. And also the laboratory was not equipped with servo actuators, and computer-controlled actuators, none available. Well, no way to do hybrid simulation, but that's not true. Necessity is the mother of invention. Using most conventional devices almost available anywhere in the structural lab, we are able to do hybrid simulation. In which way? Like this. First, we use, very conventional jack, probably all people know, using manual pumps, push and pull. Then low cell with strain meters, then to measure the reaction forces. And dial gauge, then measured by eyes, human eyes, and then the spreadsheet and the calculator. Of course, pencil needed, okay? This is before PC, once again. So these are the right components that we need to do most primitive, hybrid simulation. Now, extending this, I made a story of a Jack and Meg story. Now the story is as follows. How using such primitive devices, we can do hybrid simulation. Okay, first, okay, 2 persons, Meg and Jack. Meg is in charge of measuring and calculation. And Jack is in charge of checking, they say applying forces. First, Meg tells Jack, okay, so-and-so centimeters for the next step. Then Jack starting pumping soils, monitoring digital gauge to see how it moves and to get to the right displacement. And Jack stops pumping and he yells to Meg to measure both of them. Then Meg reads signal, writes it down on the sheet, and hits on the buttons of calculator to solve equations of motion. By repeating this, I think we are able to do hybrid simulation. Of course, not real time, but this way. And then Now, some of them say maybe skeptical about it, but that's real. It was not a joke. And we wrote in a journal paper in which Jack and Meg's story was presented explicitly. It was published in Earthquake Engineering Structure Dynamics. It's a pretty high impact factor journal. And then it was not yesterday in 1995, 30 years ago. So this is what we did. And of course, the complete manual operation was replaced by some sort of optimization using 1990s technologies, such as instead of manual pump, using a mechanical hydraulic pump, and this pump motion is sort of controlled by PC, and measurement similarly using data logger or PCs to store the data and so forth, and by introducing another computer and to come to solve the equations of motion. Then I think, manual, not manual, but inheriting the spirit of manual operation, we did it. And then, using this, now we try to simulate the earthquake response behavior of 10-story structure with hysteretic dampers embedded. And then those show some of the scenes, and then the right bottom shows the displacement history and so forth. We came up with beautiful results. Of course, in essence, there are many dark sides of the stories. So many millions of mistakes and others, but today I only show the bright side. But anyway, this way, it's possible to do that test hybrid simulation without electronic sub-actuator system. That was what I did when I switched from a big one to small one. Then it came to the shake table. Now our university got some fund to develop a 3 by 5 meter 3D activation, and characterized 1.5 meter of the second, the big velocity, that the medium-sized shake table. And at the same time, we also get dynamic actuators, also capable of applying relatively large velocities. You remember after Kobe, big damage, I think the large velocity was considered to be the source to really aggravate that degree of damage in Kobe. But anyway, now from slow to fast now. And then that was a time, 1994 Northridge, 1995 Kobe. In both earthquakes, old timers know we found many beam to column connection failures, bad, particularly in bottom flanges. So some of the pictures upstairs are from Kobe, and then bottom flange and always it's a brittle failure and separation. And the bottom line, lowest bottom floors shows the damage from 1994 Northridge. But anyway, a lot of, and then at that time, one argument was, so-called the rate of loading effect might have been a cause to such failure. What is the rate of loading? Commonly, to quantify, the beam to column connections performance, we apply forces slow, slow, slow. But the reality is bam, bam, bam. Material coupon test, boom. So when we load slow, we get stress-strain relationship somewhere here, but the same specimen, but when we put fast, yield force strength tends to go up, but the ductility goes down. So then, somehow showing the brittle behavior, that might be the cause to cause much fractures, many fractures after Kobe or Northridge. So to quantify this or to verify if this is true or not, we use this newly bought or acquired actuator, making two identical specimens, same. And the method is simple. One apply forces very slowly, and the other, and the same specimen, I mean, the same configuration, but with the fast speed, realistic speed, bam, bam. And then what happened? The one on the left shows quasi-static result. The one on the right shows the dynamic results. They both look okay, but if anything, the one dynamic was found more ductile. That was contrary to the earlier belief that the strain effect may reduce the ductility. Why this happened? Now also, say, when we saw the fracture surface, quasi-static, some brittle fracture, the portion of the fracture was brittle. Otherwise, dynamic one, very smooth, all ductile fracture. Why this happened? That was the temperature. Dynamic loading, bam, bam, bam. Hysteretic energy dissipated, but dissipated energy where? They should go somewhere, right? Then was transported to the heat energy. So this means that the temperature in the vicinity of the yielded zone can continue to rise and impossible to touch any longer toward the end. But of course, the same displacement history. But if we apply the load so slow, then I think the heat energy evaporate to the air, to the atmosphere. So then the dynamic loading test revealed that earlier speculation that fast speed, more brittle is wrong. But at least we have nice time to discover at least something different from the common sense. But anyway, this is the dynamic and still some sort of small laugh. The last one is an E-defense shake table. And for all strange reasons, I was asked to join as a director of this facility while maintaining the professorship in Kyoto University. By the way, the E-defense shake table is a jumbo shake table of 20 meter by 15 meter implant activated in all 3D and owned by National Research Institution somewhere. And then this is a configuration, big shake table of 700 metric ton chunk of mass supported by 14 vertical actuators and 5 horizontal in one direction and another 5 in the other direction. And then those under synchronized control, they produce the big motions, motions on the top of the table. This shows the specifications, but forget about those small numbers. The essence is it's 20 by 15 big. And the payload means that 1,200 metric ton of the mass could be installed on top of the table. And then the most notable was that the maximum velocity was 2 meters per second. Again, at that time, we were so obsessed with the speed, the velocity. But anyway, this is the E-defense shake table. And then since 2005, oh, by the way, this was inaugurated in 2005. And over 100 full-scale or large-scale tests have been conducted for various structures. Here, 4-story base isolation, 6-story reinforced concrete, 2-story wood, 4-story steel frame, 6-story wood houses, and the pile foundation and so forth. So pretty busy after the inauguration. So then I show you just one video here. If the video works, chance is less than 20%, considering the trouble we have encountered thus far. But nonetheless, I am right. I think it doesn't work. Can you help? You just push the button. It's
I got you. I got you. I see here.
In case of some. Okay, 4-story building. Don't worry. From another app, it's coming. See, 2 span, 2 bay, 2 span, and this first, second, third. The objective of this test to reproduce collapse. All same motion from different angles.
Pause you for a second. I'm going to get us on the Zoom so that people on the Zoom can see it. Because I don't think they can see it.
Oh, I
So,
see.
yeah. So,
Okay.
let's see.
In the name of fairness, I
Yeah.
think we have to repeat.
Yeah. I'm going to share because I want to share the whole screen. We were just sharing the presentation. And then we'll get you. So. I got you. So we'll go start from here.
From inside.
Okay.
Okay, and then return to the
Yes, sir.
PowerPoint.
Okay.
See, this is the objective is to reproduce the complete collapse. And say we really worried, but in the end it became a success. But then say this is one of them. By the way, say very loud sound, and I could repeat without sound, but then no interest. Okay, sound has a really positive impact. Okay, please remember this. With sound, it's fine. Without sound, it's soda without anything, right? But anyway, where we are. Okay, here. Now, final collapse is by the 4-story collapse, story drift collapse. And of course, I say we followed our practice of strong collapse, weak beam. So therefore, until the very end, okay, very stable behavior. But in the end, something happened bad. Always sway and so forth. But then one more story is we conducted, in parallel to this big test, we conducted the blind analysis competition. What is that? Now, say this, my specimen says, I'm ready to be subjected to big ground motion and I am to collapse. Okay, please predict when I collapse and so forth. That's the question. And then the competition is, and it was conducted. We found that participants from many countries worldwide, and the application was done through website. And of course, the purpose is please estimate and predict my life as close as possible. How the simulation can trace the experimental behavior. And we set up the 3D, 2D research individuals and engineers and so forth. But anyway, so overall, interestingly enough, over 100 teams made registration. And eventually 47 teams, right, submitted their results. And Japan 17, US 15, and so forth. Here's the result. Interesting. The one on the left, vertical axis says maximum displacement, say they predicted. and normalized by the true maximum displacement. And then 1 means bingo, and 0 means very small, underestimated, and several 100% means overestimate. And then 47 teams, I think, plotted from the smallest displacement prediction to the largest displacements. This disparity is something. And so sometimes they overestimate by the factor of 7, or sometimes they said that the maximum displacement is 0. How come they can come up? But nonetheless, say this big disparity we found. And a good example is here, and pretty good. Later, one of my postdocs did careful tuning of hysteretic models in reference to the experimental results, and like the tuning of beam behaviors, tuning of column-based behaviors, with all kinds of tuning done. Look, experimental behavior to the collapse, and it was completely simulated by numerical simulation. So the greatness of numerical simulation, with a reservation that numerical simulation is great, but only after we discover the actual behavior, and particularly when the behavior involves a very strong nonlinearity. A little sarcastic, and I'm accused by numerical analysts, but nonetheless, this is something that we have discovered. Now, okay, so I have introduced all 4 facilities. You remember? Okay, and then besides, we did together with my students small pieces of study on various aspects of hybrid simulation, like errors propagation. Sometimes error create big problems, or hybrid simulation with substructuring techniques, or the peer-to-peer internet online testing, or simulation with mixed control, or toward the end, real-time hybrid simulation. One time we we tried using the 1980s technologies, another time in 1990s technology, and so forth. But in the interest of time, I just skipped those. Afterward, they are not important. But anyway, red shows which lab I used to come up with those developments. And then in 1980s, 90s, until probably mid-2000, very few people engaged in hybrid simulation. So therefore, it was easy. We could do anything we want without being bothered. But anyway, this is the time. Also, some sort of developments regarding the experimental techniques related to shake table tests, like substructure-based shake table test, or something. But again, they're not important, so therefore I skip, except for one example. Now, there wasn't a concern about the performance and damage of high-rise buildings subjected to long period and long duration ground motions. What is that? Japan on the Pacific, so the big ocean ridge called the Nankai Trough, periodically bang, bang. When this happens, I think when those the ground motions reach like a big cities, Tokyo, Osaka, so forth, high frequency component, it is dumped out. But not so large in accelerations, but long period motion continue, and then not long time for 10 minutes. So then, biggest victims, high rises. Because of the resonance amplified, particularly to the top, and also for long duration, 10 minutes, how many cycles of back and forth of loading, so fatigue failures may become a concern and so forth. But anyway, long period ground motion was as a topic to consider. Then we decided, we tried to do it using e-defense, but 20 stories high means over like nearly 100 meters, right? Say the largest facility, our ceiling was only 50 meters. Then if we develop the real scale specimen, it will penetrate into the air, and that's not possible. Then, however, we still want to do that. We squeeze the upper portions like this. See, civil engineers, you understand how we treat it. So the one on the right shows the bottom 4 stories. We reproduce as it should be, means beams, columns, floor slabs, everything. But with the expectation and with the knowledge that the lowest 4 stories will sustain the largest deformations anyway. And then the above one, few stories condensed into one, another few stories condensed another. So then mass condensed and then represented by reinforced concrete panels or slabs. And the stiffness wise, say a few stories, say the stiffness adjusted and then replaced, represented by rubber bearings and with dampers and so on. So damper, rubber bearings, floor slabs, and then try to reproduce the first mode, natural frequency, second mode, third mode, and fourth mode, and so forth. Try to resolve the dynamic characteristics as close as possible to the prototype. This is what we did. So in order to save the life of our ceiling. Anyway, so the one in the middle is the specimen that we use. It is scary, see, big mass times 4 on top. And of course, they vibrate, means that the top doors, a big mass moving more than 2 meters back and forth. Ooh, that's something. Not good for the health, but particularly for the director, but that's okay. All right, so then it was a success. Look at that beam to column connection in lower stories, the significant yielding in elastic behavior, and some of them that were shown in red and in yellow, apparently bad. And the fractures happen to beam to column connections and the significant loss of resistance and so forth. These could have been, could be, say, reproduced, which was fine. So this is one. Okay, and then here, one lesson I see. We always encounter project, a new project, whose test demands something beyond the facility's capacities. For instance, say if the table is 20 meter by 15 meter, say researchers come, say for specimens, say 16 meter by 21 meter. Okay. And therefore, maybe we may say enlarge the size of the table. Then the next day they'll come a little even larger. So it's say research individual pretty insatiable. But anyway, this is so therefore the size is sort of endless. Now, the final thing. Now, time okay, I don't control any longer, sorry. I think I started like 1940, 449. Okay, I'm trying to finish as fast as possible. Now, final stage of my presentation, okay, size and scale and time and so forth. See how size affects experimental results. Probably many of you know already. Difficulties in duplicating details in reduced scale specimens. Like a building frame in the middle, say in the numerical analysis, oftentimes beams and the columns aligns and the connections are just a point. But reality is reinforced concrete, it is not a point full of reinforcing bars in both horizontally and vertically, or in steel structure and beam to column connections, say we weld, but the weld details like that, say many layers of welding to connect the column and the beam and so forth. But now it's easy to say that, sorry, we can't scale down those details. It's small enough from even in the prototype, how come we can further reduce? Then one simple example. Beam to column connection, bam, bam, bam. See how the connection behaves. And the one on the left is on the full scale. And the one on the right is 1/10 scale. See, then we fabricate the specimen, machine cut carefully. And then, however, the connection of the beam to the column was impossible to weld because the thickness of the flange was less than 2 millimeters already. So therefore, we cheated the connection by mechanical joints. Then what happened? She said the one in the real scale, ductile behavior, but somewhere it breaks. It broke. That's it. Otherwise, by cheating the connection by mechanical joint, the results says that the beam to column connection is infinitely ductile. So therefore, this tells that the size reduced, difficult to duplicate the prototype behavior. And then redundancy issue as well. So this is a very small scale, I mean, full scale, but 2 by 1 bay, very simple steel moment frame. And we did static test, push and pull. And then one time, beam to column function, bang, the one on the left. But then if it were an element test, beam to column connection only, bang, this is the end of the test because separation, that's it. However, if it is integrated into the frame, as you see on the right, the fracture bang probably cause a drop of 20% of the force. But if we keep pushing, then of course the stiffness reduced, but basically stable. So then we push, and then to the desk. But the form of the failure, I mean, collapse mechanism was changed from, again, strong beam to, strong column to weak beam, type 2, the first of the shear. But anyway, so the redundancy issue, of course, is something to do with the capacity of our structures against collapse, so forth. So now, the final question, which one of them do you like? Slow, fast, small, big? Which combination you like best? Now, to this end, we have to think. Element size, beam, full scale versus reduced scale. Reduction in scale is okay. Rate of loading. Earlier I said, bam, bam, bam versus intentional slow. Is this important? Or redundancy? One member versus much redundancy. Type of loading, I did not touch upon, but I think, oftentimes, the structural tests in earthquake engineering go with small cycles, I mean, amplitude, fixed amplitude, some cycles, increasing the amplitude, some cycles, increasing further, and so forth. So it's a typical cyclic loading test. But the reality is sometimes one, big, small, and so forth. Then lab availability, big lab, small lab, cost of experiment, that's obvious, or public attention, appealing to media, or very professional. Important, right, as a test, but nobody understands what they are doing. Or some of the tests very appealing, and then the e-defense, some tests televised in so there are many issues to consider. And then at least to consider which one you like. One trend I discovered. Now, earthquake engineering research community has 2 groups, okay? Basically into 2 groups. And there is a chasm, okay, or war, whichever, between those 2 groups. Now, which group do you belong to? Now, what you mean by groups? One group is supply side people. Another group, the other group is demand side people. First, demand side means, say, in earthquake engineering, the ground motions. But we have then forces, inertial forces exerted into the structures, and the structure have to sustain those forces without collapse. So then how much of the force we have to consider and how they behave? It's okay. So some people's main interest is this. So I call them demand people, dynamics and so forth. Otherwise, supply side people means suppose this much of the strength needed for my structure, how we design, how big the specimen, columns, beams, and connections and so forth. Then to make sure that the structure is strong enough not to cause any damage and so forth. So supply side people, capacity-oriented people versus demand-side people, response-oriented people. Those two groups are different. And then they like analysis, on the demand people, or the supply side people probably say prefers, I think, at least place more emphasis upon the test. But anyway, say, if anything, supply side people like strong flow and wall systems, slow one. Otherwise, demand side people like dynamics, means shake tables. So this is how I view. What about the small versus large? And then to this end, I did some statistics. As a university professor, I fortunately survived and supervised about 60 PhD students and postdocs and about 100 graduate and undergraduate students. And I was able to publish, say, probably 200 plus journal papers. I was lucky. But I checked how many papers are produced by each testing facility. Then I took the statistics, big and fast, 27, big and slow, 8, small and fast, 26, small and slow, 86. By far, okay, small and say slow, you say, well, most productive in terms of the number of publications. Said, as a university professor, I see my mission as nurturing the next generation and consider research a means to education to develop students' insight. So in this context, probably I shall value the contribution of small and slow. But this is my subjective view, and this is my, and all individuals engaged in research and education, they should first define their ultimate missions and then review which combination will bring you most tangible benefits. That's how I feel. But so I said small and slow, but big and fast, and very important. Occasionally, we have to resort to the ultimate solution. So therefore, ultimate solutions big and fast, or also big and slow and so forth. So again, depends on individuals' preferences and their respective missions. That's how I see this say slow versus fast, which you say prefer small and big and slow and fast. Now, so this is the more or less the end, and then I showed a few pictures. The one on the left, Fritz Lab, 1970. The 77, and the same, right? Not much of the change. And they say, look at that, the automobile, say in the front, is my 1970s automobile Catras. The one on the right shows my office, room 203, no longer existing. And then look at that, my desk and my shelf doesn't carry any textbooks. That's bad, but let's forget it. Okay, and then there is no computer, right? Instead, someone see the one in the middle, it is called a typewriter. This is the age I enjoy my life in say, Lehigh University, or say some nice reunions. Lehigh, Professor Rickles and South, came to my institution, 20 years ago, or lower one, a little young, Professor Fisher in the middle, the one on your right is Professor Joe Ura of University of Texas, and myself, Pelly Green, and Gilbert Areza, and Tom Fisher, my classmates, all get together in one of the steel conferences and so forth. More pictures. Bruce Johnston, Lynn Beadle, those legendary names. And it was the picture taken in 1973. I did not take the picture. Someone gave it to me. The guy called Ted Galambos, 19. And then, or Wyfer Chen, those Lehigh alumni. Or the one in the middle, Professor Yushi Fukumoto, Japanese famous professor, also Lehigh alumni. Those boarding face, I think that's Professor Igor Popov, Professor Jim Rick was the teacher. But anyway, with those nice fond memories, and my closure is, I wish Lehigh Civil Engineering every success and probably next generations of education institutions. This ends my long story. Thank you so much for your kind attention. You ignore?
Any questions from the audience?
No technical question allowed. What is that? Yes. What do you mean by next? Next, the future. My future. Now, my future, I'm presently right research like devils. But okay. Research engineers. Me, I want to be a good team. So therefore, as long as I like things, I will behave as a team. Thank you. Yes, and you did a lot of earthquake stuff, being in Japan. You also work with tsunamis as well. Did anything else? Tsunami. Okay. See, I have not done anything with tsunami. Yeah, because tsunami is, of course, they come together, but very different behavior. Right? Basic equations and it's a capability. So then I think it's a multi-custom, particularly like tsunami after earthquake or fire after such. Those are really important problems to resolve. And then our Japanese community, society feels that we have done many things, but not sufficient. So therefore, there is a big group to explore the combined disaster. And within the domain of like fire or those are important, very important subjects. But for better or worse, my academic life is ending, so probably I will rely on you. Okay.
Maker, so go ahead.
Thank you for the presentation. Very nice. Have you ever considered testing soil structure interaction with your real-time relationship?
Yes, although I have not shown, but we have a relatively large soil box, okay, permanent soil box, 15 meter to 10 meter, and then by adding soils and so forth. Yes, we did try more than half a dozen soil structure interaction tests. But see, soils, see, gravity similitude is very difficult to maintain. As a result, see, geotech engineers do not necessarily say, appreciate shake table test. These days, their preference is centrifuge, right? So some some arguments needed, but at least on the surface, my answer is yes. We have done say half a dozen soil structure interaction tests, including like a liquefaction and so forth. So I think we could do the test. The reliability of the test is something else. Okay.
So you mentioned all these different methods, right? But you mentioned all these different methods like shade table versus hybrid simulation.
Mm-hmm.
So what are your thoughts? I think you could combine both. You know, there's
yeah, he is correct. I think that I intentionally did not say much about the hybrid simulation today, and then because of the time and so forth. But hybrid simulation and with I mean real-time capability, and also I mean say, accurate control with many degrees of freedom, then I think that this may be a great replacement of shake table test. However, say in terms of the public appeal, I think the hybrid testing probably not possible to beat shake table tests on a realistic size. Everyone, okay, my grandmother even understands what it is. But anyway, say hybrid simulation, particularly real-time capability, substructuring, and multiple actuators, sounds a little too professional. Therefore, I intentionally did not include. But anyway, I think this is something you should do it anyway. Okay, and it's over to you. Okay.
Anyways, I'm going to read you a question here. Sorry, I don't know if there's any other question on this, but we're also on Zoom, as you may have figured out. You see the question, but I'll go ahead and pose. It's actually two questions. One is from Hosan Ahmadjidian. Sorry if I mispronounced your names. First, thank you. I would like to ask, how is AI currently being utilized in real-time hybrid simulation? According to yourself, Professor Nakashima, enhance accuracy, efficiency. What does you see as the most promising future applications or breakthroughs in integrating AI with real-time hybrid simulation?
So, unfortunately, I'm not in a position of answering to this question because, honestly speaking, I have not been so much engaged in hybrid simulation for the past 10 years, all the while AI is a new technology. Professor Ricus, can you help me?
So AI is just an interpreter. You establish boundaries, you model something with AI. It's usually what's called neural networks, and you could run these models very, very, very fast because they're reduced order, but higher level, versus trying to model, say, all that soil of 1 billion elements. You can come forward in maybe 6 nodes. Imagine how much faster you run it. The reason you need to do this is because when you do things in real time, you have to do real time. The time steps sometimes are 0.001 seconds. That's really fast. So AI is good, but there's a lot of issues with it. So it could be done. We're actually doing it up at Atlas.
I may be asking the answer to a wrong person.
Sorry.
He is too professional. Then I think another question.
Yes. Sorry. So very, very nice talk. We have a first-year PhD student. This is Hongyo Zhang. Could you suggest systematically identifying a research direction that is meaningful, high impact, and deep enough for several years? Could you share 2 or 3 principles from your experience? All your secrets.
That's right. This is secret, and this is something we should not share. Otherwise, the life as a research individual stays for shorter time. This is something you discover for yourself. This is a surface answer, and then the real answer is very difficult to systematically identify research direction. How would you suggest that is meaningful, high impact, and deep in several years? But see, me engaged in hybrid simulation, but it was See, very few people are doing that. Say when I started, then I never knew that the hybrid simulation became so popular. So therefore, impact or meaningful, say at the time when we began, probably don't know. And we may be lucky, we may not be lucky. So however, persistency is important. Once we start, probably we continue, no matter how unpopular this is. So probably, sorry, I cannot, this is not a direct answer, but that's my honest impression, sir. Thank you, Mr. Jan.
Okay, is there any other
Yeah.
questions from the audience?
Yes, I'll just read here. The next one is Shivam Sharma. Based on your experience, in which cases is it unacceptable to apply quasi-static loading to simulate earthquakes?
Quasi-static testing incapable. Okay, probably if the structure, concerned structure, say is equipped with like time-dependent, say velocity sensitive, devices, materials, and so forth. Otherwise, to me, size is more important than the velocity, as long as we use conventional materials such as wood, steel, and reinforced concrete. But if we start dealing with time-dependent, right, materials and devices, say quasi-static loading test does not give us any. So then answer is relatively straightforward, as I said. Okay.
And then there's another one in here from Pedram Mardazabe. It says, with regards to real-time hybrid simulation, fast real-time hybrid simulation, in your perspective, is this classified as a test determining capacity or demand? That was the first one.
Oh, I see. See, to me, even real-time or non-real-time, this hybrid simulation is basically on the demand side rather than on the capacity side. The beauty of hybrid simulation is the same loading system is able to do both. In other words, can satisfy the needs of demand people, bam, bam, bam. It's dynamic things. But at the same time, this can satisfy the needs of the supply people. How to ensure sufficient connection. Then to verify it, we can use the same testing method, facility to quantify this. So therefore, short answer is, hybrid simulation in general is for demand people, not demand side. But the same device, facility can be used for supply side as well.
The same person followed that, hypothesizing that perhaps somewhere in the middle, depending on the test design, the size of it, would be reason for you. So kind of along
Thank
the
you.
lines.
Yeah.
Want to read the next one?
So there was, sorry.
Oh, we have an audience question, please.
I was wondering if there's a way to kind of simulate the effects of two mass dampener within quasi-static simulation.
Sorry, I didn't hear you.
Sorry. I was wondering if there was a way to simulate the effects of a two mass damper in quasi-static simulation.
EMD behavior and probably quasi-static loading effects. Will not give any. We have to go through. Let me get this one.
Do this, but it comes down to rate dependence. If anything is rate dependent, depending on the law. And this you push on something is depending on how fast you push it over the other. If the push on it was loaded, the real time is really important. For the EMD, they have a dash pilot, you have the vehicle loss of penalty. Testing loss of the time. Otherwise, you can slow things down. But the other problem you can get with quasi-static testing is the coupling between the device and the structure and the realistic demand of the structure. And that hybrid simulation, you get that really tightened down where you want. You have to be, it could be 3 miles at each side of the node, the whole city, you don't want it.
Okay.
There's one on the screen for the
You want me to read it for
you
you?
guys can read that.
Is there still a need for building large-scale facilities in the United States? Still a need. What kind of needs that still need to be addressed? We should say a new large-scale testing facility or
Bigger pictures.
including capacity and simulation testing. See, definitely we like to have large scale labs, yeah, to get the ultimate verification. But how often we have to do that is a matter of debate. So therefore, see, if the number of tests required is not so large, then probably existing facilities are good enough. So then at least say the facility must be open to the old people. Then say sharing or like that. So because say the current US system, like big labs, I think that say this is what you're doing, right? You can other university, I mean researchers in other institutions can still make use of like for instance, the Lehigh University's laboratory and so forth. So then more needed or not, I don't know. But at least some needed. But then see the number of those big facilities sufficiently many or say yet to be built and so forth. That's different. Yeah. But anyway, say I am not a US citizen, therefore I don't have to commit myself to anything. But anyway, I say I know that I have not given a full answer, but this is the most I could do for this particular question. Okay. Yeah. Yeah. Okay. But probably.
All of research is dollars. How much it costs them? You've seen those shade table tests. At least $4 or $5 million a test. Very expensive. So the question is, you have to build up the thing and test the whole thing. It might take 2 years or you do something else. My answer is yes. It's called hybrid simulation. Whatever you can model numerically, there's no need to test physically. But then you can't model it numerically. So what you do is you model and numerically, and you take in the system and model that physically, and then you join it, you get the whole system. And that's very efficient. And that's what the government's actually looking for right now, is efficiency. So that and multi-physics. So earthquakes very important, but there's other elements, especially on the East Coast. What is it? Hurricanes, fluid structure interaction, soil structure interaction. So those are, to me, that's the new frontiers in hybrid simulation and earthquake engineering.
You're cheering. You have to go. When we stop, or I think probably 2,000 people going to bed. Yeah. Okay. Oh, thank you.